في حاجات لازم اعملها.
طب
اوكي،
يعني
خليني
ابدا بالشكل.
ثانية واحدة بس، انا هشوف اقدر اعمل ايه من هنا. ثانية. آه... اوكي، فيو سبيكر، في جاليري، في مالتي سبيكر، في كده مثلا. is that something that's هل ده احسن ولا لسه نفس المشكلة؟
نفس المشكله، وحضرتك ممكن ما تعملش يعني ممكن ما تعملش فول سكرين خالص، يعني ممكن تشتغل بالشكل ده.
يعني افضل انه اعمل ال مم. اوكي. set. ثانية واحدة. هل ده عامل اي فرق ولا لسه نفس المشكلة؟ عندك نفس المشكلة؟ الو.
هي نفس المشكله، بس في مشكله بالنسبه لكم كده. طب ممكن تشرح كده يا دكتور جهاد؟
اوكي. آه ماشي. it's better
نعم.
طبعا انه انا اعملها بطريقة تانية، لان في حاجات فيها زي انيميشن. فلما نيجي عليها هبقى اعملها فول سكرين
طب
يعني.
طب بص حضرتك، اعمل فول سكرين كده، او
طيب.
اعمل سلايد شو.
اوكي،
اضغط على
that's
سلايد شو.
like. اوكي.
ال ال طيب، في 3 نقط في الدايره، ايوه بالظبط كده.
ايوه. اوكي.
شيل هايد بريزنتر فيو، بس كده. اوكي.
this one.
يا
اوكي، دلوقتي انتوا شايفينها فول سكرين. انت شايف
بتجمع دلوقتي.
دلوقتي الشو، انت شايف الشاشة كاملة
لا،
يعني.
حضرتك شايفها بس احنا مش شايفينها. ممكن بقى تعمل الغاء الشير وتشير تاني.
اوكي طيب.
الشير
ثانية.
وشير تاني. الشير بس مش الباوربوينت.
اوكي، ثانية واحدة. اوكي، ستوب شير، وبعدين اعمل شير تاني. اوكي. اوكي. تمام. اوكي. تمام. دلوقتي ايه
بالظبط.
بقى اللي انت شايفه؟
جو اهيد، بالظبط كده كده، اكسلنت. جو اهيد.
كده عندك فول سكرين.
كويس جدا، ممتاز.
اوكي تمام. ماشي. اوكي. بيرفكت.
انت
طيب.
شغال كويس جدا.
okay. So can everyone hear me well? Can you see my presentation?
يب جو اهيد.
Okay, perfect. طيب. طبعا what we did already, Professor Hisham went
معلش،
over like an.
انا استاذنك، حاول تخلي الشرح بس ميكس عشان يحاولوا هم يكابتشروا الكونسبتس بس.
إن شاء الله I will do my best. طيب. The thing is, if you wanna learn about quantum computing, إذا عايز تتعلم عن quantum computing and quantum information, you have to know good quantum mechanics. This is something that you cannot escape. Yeah. So basically, what we are gonna do here, I'm gonna try to go deeper in quantum mechanics, teach you the basic things on quantum mechanics, so that we can understand why quantum mechanics is important when we talk about quantum computing. Inshallah. So the very first thing اللي احنا محتاجين نتكلم عليه هو what happens if you basically okay. Do you see the new slide, or because I feel like the slides are not okay. Can you see my slides, the new slide? Everyone?
يس.
Yeah,
جو اهيد.
okay.
جو
Good.
اهيد.
Okay. طيب. احنا في الكلاسيكال وورلد، في العالم الطبيعي الكلاسيكي اللي احنا عايشين فيه, what we do usually is we study objects that we can see. We study their motion, how they start, how they evolve with time. ازاي بيتغير البوزيشنز بتاعهم مع الوقت. فزي ما كان briefly Professor Hisham explained, basically if you know something about your particle, like where your particle started. Like if you have, for instance, here you are starting at t equals 0, and you know very well what is the initial position. Like I'm gonna call the position at this time x0. And you know what kind of force is acting on your object, which is a car or something similar to that, with a mass m. So the question is, what happens when you are at a time t? And the way we do this is by solving Newton's second law. Basically, it's the equation of motion for the mechanics. So I'm having an object, and that object is under a force F, and I can tell at the time t what's going to be the position as a function of time. فأنا لو أنا عارف الأوبجكت بتاعي started فين we started at which time, I can tell what's going to happen in the future. So that's the main idea when we do classical mechanics. So it's basically, it's like a machine where we are simply having, it's like a machine, which is Newton's second law, which we all know. So second law of Newton. So basically, I know that it's F equals ma. That's the equation that we all know. Even you know it from your high school. So it's not something that's advanced. And the thing is, I can basically do the following. I can feed this machine. بدخل على الماشين دي انه انا at t equals 0 عندي x كانت بتساوي x node. And afterwards, when we have this going through this machine, it's gonna give me x at the time t. إذا أنا عارف what is, if we get this piece of information, like I know what x of t is, I can get the velocity, because that's very easy. If you take the derivative of x, as we know, you get the velocity. And if you basically multiply the velocity by the mass, you get, so mv of t is basically going to give me the momentum, as we all know also from even high school physics. So the state of any particle, and that's the thing that we have to know, state of particle, state is determined by two things, is determined by the position at time t and the momentum at time t. That's what we do in classical physics. If you have an object like a particle or a car or a ball or anything of that type, it's so much enough for you to know the position and the momentum to tell what's the state of that particle. لو عندي كورة بتتحرك في غرفة, I can tell where, if I can tell where is the position and the velocity, which means I know the momentum. At any moment, I know very well the state of that particle. So that's the thing. Now, in the quantum world, things are completely different. That's the thing that we would like to stress on here. When we do things in the quantum world, if you have, for instance, an electron in a box, imagine that you have an electron, you have a box here, and inside that box, you have an electron with mass m. So basically, how you determine the state of that electron. So this is, let's say, an electron. The thing is, it's completely different from what you do in classical world. In quantum world, what's going to happen is you are going to describe the state, الحالة بتاعت هذا الإلكترون, using what's called the wave function. So basically, I'm going to have, okay, to draw a psi of that particle, and it's going to be a function. So that's at a certain time. So let's say at t equals t1. And psi is going to be a function also of x. So psi is a function of, at certain time. and it's also a function of the position. How does psi look like? Psi is a wave function, so it's something like that. You can imagine that it's something like that. Okay? And so your electron is not treated as a particle. هو مش جسيم anymore. انت بتتعامل معاه على انه wave، وهذه الwave is expanded in space from here to here. Okay, so I'm gonna call this, let's say, x1 and x2. And to be precise, as I said, basically, I'm gonna call psi as a function. Okay, as I said, psi here is a function of the position and the time, but I'm taking certain time. So at certain moment of the time, this is how the wave looks like as a function of x. Okay, everyone? So this is the story. Now, why this is important? Okay, where is my particle? Where is the electron? It's everywhere between x1 and x2. Okay, so it's not at a specific point at this moment. It is expanding itself as a wave. So it's existing everywhere between x1 and the x2. That's the thing. Okay, so someone may say, oh, what are we talking about here? Is that guy is a wave or is it a particle? We will answer that in in a moment from now. حالا يعني السؤال الكبير هو هل الالكترون بيتصرف كبارتيكل زي ما كنا بنعرف انه اي جسيم او جسم في الكوانتم في الكلاسيكال ميكانكس بيتصرف ولا بيتصرف كويف؟ It's a very good question. وايه معنى الويف? What does it mean that you are describing the state of the electron using a wave? What this is going to tell us. Actually, at this moment, someone will say, okay, where is my electron? Is it, is it at this point or that point or that point? It's actually everywhere between x1 and x2. And this is the big question. Is an electron, okay, is an electron a particle or a wave? Okay. Actually, it has what we call it dual nature. عنده طبيعة مزدوجة. It acts like a particle and it acts like a wave depending on what are the environment around it. So it has a kind of schizophrenia. عنده شخصية مزدوجة. This is what you have to understand. It has this dual nature. The thing is, okay, in classical physics, an object like an electron is treated all the time as a particle. When we come to quantum mechanics, actually, and as I said, you have to use Newton's second law to describe that particle. So if you have a ball in a room, how you describe or how do you understand its motion? You have to apply Newton's second law. If you apply Newton's second law to that particle or that ball or that object, you can actually get all the information you need about what's going to happen to that in the future. إيه اللي هيحصل له في المستقبل. In quantum physics, as I said, I'm going to describe my electron as a wave. And basically, the amplitude of the wave tells me what is the probability that the electron can be found here if we make a measurement. احنا زي ما قلنا, I have an electron in a box. Someone is coming and say, okay, I want to actually determine, أنا عايز أحدد هو مكانه فين. You have to make an experiment. You have to make a measurement. If you make a measurement, okay, you can find it at a point. So when I do a measurement, where I'm gonna find it? Actually, I don't have an exact answer for that. The probability to find the electron when you make a measurement is proportional to this amplitude here. Okay, so the amplitude, okay, as you can see here, the red arrow here, السهم الأحمر ده مديني الامبليتيود بتاعت البارتيكل بتاعت الإلكترون في المنطقة دي. There are places where you have zero probability. علشان لو احنا الويف عندها نقطة بصفر مثلا زي دي، يعني مثلا انا عندي هنا النقطة دي مثلا بصفر. This is zero. الويف عندها قيمتها بصفر. So there is no probability ان انا الاقيه هنا. There is no probability ان انا الاقيه هنا. يعني ده صفر، ده صفر كمان. Right? This one too is a zero هنا في النقطة دي. But this is high probability. Okay? So this is how things are. This wave is telling me if you make a measurement to find the electron, okay, it's telling me where it's very probable to find it. احتمال الكبير الاقيه فين. كل ما الويف الامبليتيود بتاعتها تبقى اكبر في منطقة، ده معناه انه انا have big probability to find it there. That's the thing. I have to make a measurement. ولما اعمل measurement, when I do the measurement, I'm gonna find the electron somewhere. But where it is, I'm not sure at the beginning. All what I can tell you is probabilities. Do the experiment, okay? Do the experiment and basically see where it's gonna be. And so high probability here, low probability here, okay, as you can see here. And the wave function is a kind of a mathematical tool to tell me if you make a measurement, where to find the electron. Okay. As I said, the wave function is a mathematical tool. I don't know where the particle is. It's existing for sure between the beginning, between the beginning of the, like between, for instance, this point here. I mean, I'm sure it's between this point here and this point here. It's somewhere between this and that. At the beginning, I don't know where it is. I know that it's everywhere actually between these 2 points. Like this is the like x1 and this is like my x2. It's somewhere here. Now you make a measurement and you are gonna find it somewhere between these 2 points. Very good. Who controls what happens in the quantum world? As we said, you know very well that I don't know if you can see my cursor, السهم بتاعي تقدروا تشوفوه ولا لأ. We said that in classical physics we
احنا شايفين الكرسي كويس.
طيب ممتاز
احنا
جدا،
شايفين.
ده كويس جدا. فاحنا قلنا in classical physics you can apply Newton's second law, and if you apply Newton's second law, basically you can tell everything about how the particle is going to progress in time. If you look at the quantum case, what is the equation that governs what happens? It's actually Schrödinger equation. Schrödinger equation, do not get scared. It's a differential equation. I don't know if you are familiar with differential equations, but if you look here to this guy, this is itself is a differential equation, by the way, because you have a derivative, okay, for x with respect to t. And by the way, if we know classical mechanics, the force usually is equal to negative the derivative of the potential energy of the particle or this guy with respect to x. So I can write here, this is partial v by partial x, where v is the potential energy of the particle or the object that you are looking at. Here, I have a very similar thing. This is again the potential energy of the particle I'm looking at. And here, this is my wave function. How is it changing with time? d psi by dt is given by how it changes second derivative with respect to x plus v times psi. This is the Schrödinger equation that we are talking about. Okay, so now why this is important? If we go back, I'm stressing on this because this is the key point for everything about quantum mechanics. If you go back here one more time, if we go back to where we started, basically, okay, here, as I said, Newton's second law, if you feed Newton's second law with the initial position, and if you feed it with your initial position, at t equals 0, you can get x at any time t, and you can get all the information that you wish about the system. Here, it's very similar. If you know, so let me explain that here. If you know very well, okay, so this is Schrödinger equation. This is the quantum mechanics machine. If you supply to this machine, okay, if you supply to this machine, basically, what is the wave function at t equals 0? What was your wave function? Okay, at t equals 0, this machine is going to give me the wave function at any time t later. So if you look at this, it's interesting. Here, if I know what is x at t0, I can get x at any time t. While here, if I know how the wave function looks like if it's something like that, for instance, and I give it to this machine, which is Schrödinger equation, I solve Schrödinger equation, it's gonna give me the new wave function and how it looks like at a time t, for instance, okay, which may look like that. So in fact, you start with certain wave function. We usually call it psi 0, and we end with a new wave function that describes how my system is at a time t later. So Schrödinger equation plays the role of Newton's second law in classical mechanics. It takes how your wave function looks like at the beginning and gives you what happens in the future. So this is so essential actually in our understanding of how quantum mechanics works. Now, someone may look at, okay, at what we did already and, okay, and say, oh, well, so what are we exactly doing here? Okay, here is the thing. When you make a measurement, okay, so we talked about that already, that if my particle is in a box, actually it's described by a wave function. If you make a measurement, your wave function is gonna become a particle, like a point. It's gonna collapse to a point. So it behaves now like a particle. So look at this. So you have at the beginning this wave function describing your electron. And then you make kind of a measurement to determine where is this particle is gonna be. I wanna make sure that you get this point. I have my, okay, I have the box, and I have inside that box my particle with mass m. And it's actually a wave here. It's not a particle, it's a wave. I make a measurement on the particle. So for instance, how you make a measurement. Let's say you are shining light. كأن عندي electron in a box we described as a wave. It's spreading itself over the space. لما بعمل measurement كأني مثلا I'm gonna shine light. So you are gonna shine light at the electron. The light is a group of photons, and those photons are gonna go try to find where is your electron, and one of them, واحد من الفوتونات, is gonna hit the electron and comes back to you telling you, oh, I found it at that place. So what happens is basically you get the following. You find yourself after the measurement, your wave becomes just a point. Look at this. This is the whole thing. So we actually converted the wave into a particle by making the measurement. Okay, يا جماعة, are you following me? So this is basically the main idea. When you make a measurement, your wave becomes a particle and you find the electron in one place. This is so important to understand and to grasp. إنه لازم نفهم إنه originally it was a wave. Now when you do the measurement, it becomes a particle. So originally, actually, your electron was everywhere between this point and this point here. So it's everywhere. When I make a measurement, now my wave becomes a point. Okay, and that's the amazing thing about classical the quantum mechanics, that everyone was, you know, many of the scientists were objecting that, oh, that makes no sense. how that happens. How don't we know about the particle at the beginning? Now, the thing is, there is a very funny, so if you look at that, you have here at the left the quantum world. If you make a measurement, you end up having a particle as if it is in a classical world, because I know very well where it's positioned. There is a very nice drawing representing this. It's here. That was published in 1991 in Physics Today. It's like showing you what is the difference between having a classical world and a quantum world. Where in a classical world, everything is very clear, no uncertainty. I know what everything and where it is existing exactly. But if you jump to the quantum world, things becomes vague, becomes not clear. يعني الحاجات بتبقى ضبابية. Okay? And they write here, stop show your classical apparatus. يعني ورينا لو معاك أجهزة قياس. لأنه أجهزة القياس لو عديت بيها في الكوانتم وورلد, it will convert the quantum world or the information that we have into a classical ones. So that's the kind of funny thing that you look at. Now, people may wonder, do really electrons behave like waves? Yes. Maybe you are familiar with the double slit experiment اللي بنعدي فيها ضوء. If light, so it's I'm sorry. Let me do it here. Okay. I'm gonna show you this to you first. If you have light, guys, if you look here, this is light. Okay, if you have light and you shine that on two slits, like عندك فتحتين الضوء بيعدي منهم, الضوء هو wave. So at the other side بيحصل interference pattern. فتلاقي بيتكون خطوط مناطق مضيئة ومناطق مظلمة للضوء. Okay, فده ليه الضوء بيعمل كده؟ لأنه الضوء is a wave, it has an interference. بيسموها تداخل الضوء. شعاعين من الضوء, one جاي من هذه الفتحة والتاني جاي من الفتحة التانية, بيقابلوا بعض behind this two double slit thing, and they make interference pattern where you see basically ضوء وضلمة, ضوء وضلمة, يعني brightness وdarkness, brightness وdarkness, and so on. So if you look at this, this is what waves do. What's interesting is that when people tried that with electrons, they got it. If you take electrons coming from electron gun and you send them through two slits, two double slits, زي ما انت شايف كده فتحتين, it goes and hit this detector here. And what you are gonna observe is very interesting. If they were particles, they are supposed to look like that, like انه تلاقي الكترونات كتير في المنطقة دي والكترونات كتيرة في المنطقة دي, في كده منطقة فيها ماكسيمم وماكسيمم وفي النص قليل جدا. But what people found is that actually electrons behave as if they are waves, and they do those interference patterns where you have a lot of electrons and then no electrons, a lot of electrons, no electrons. It's exactly like the wave behavior. So this experiment was done in real life. I'm gonna show you actually that experiment here. Here, if you look at this, here they used 8 electrons. Here they used 270 electrons. They kept increasing the electrons. That was done in Japan. Hitachi lab in Japan. And basically, when they had 160,000 electrons, they were able to see this interference pattern, which shows that actually electrons behaved as waves. So that's not, as a matter of fact, that is not not a lie. Okay, let's go back to to what we were talking about. As we said, okay, you have a wave, and that wave is describing the state of your electron. Okay, so it's like that. So originally I have a wave, let's say something that looks like that, okay? And what really interests people is not psi itself, because psi has a positive and negative, as you can see. They have a positive and that it has a positive and negative sides. But if you square it, everything becomes positive. And now the height of the psi square is going to give you the amplitude of finding, or the probability of finding the particle. So as you can see, at point A, we have the highest probability to find the particle if we make a measurement. While at B, you have a 0 probability. So if you repeat the experiment millions of times, you're not going to have the electron found at B. There is a good probability here, for instance, small probability here, and so on. So the height of your psi squared is actually going to help you determines where you are going to find the electron. Okay. Now let's look at what happens. If I make a measurement, I'm going to find the particle somewhere. So this whole wave becomes like a spike. يعني الويف دي كلها بيسموها كولابس. حصل لها انهيار لما عملت الميجرمنت وبعدين بلاقيها هنا في المكان ده. Can see that? So actually, originally, the electron was everywhere between here and there. But when we make a measurement, it's gonna collapse to just a point. So it's like we found it here at point C. Okay? So that's basically what happened. So now, after making the measurement, right after making the measurement, we know 100% that the electron or the particle we are looking at is existing at point C, as you can see here. Now, someone may ask, what if we leave it for, a little bit of time? It's gonna spread out again. Okay, so at this moment, we know very well that the whole wave is concentrated. كل الويف مركزة عند نقطة C, so the electron is here, I'm sure, 100%. What if you leave it for a little bit? If you leave it for a little bit after time T, it's gonna spread out again. It's not gonna stay as it is. It's gonna have a wave form again. So this is very funny because it doesn't like to stay as a particle. It's gonna spread out again. And if someone asks you now, where is the particle after like a few seconds or if even a millisecond, you will say, oh, it's now spreading out. I don't know where it is exactly. Okay, so this is so interesting. But what if I make a measurement immediately? What if I make a measurement immediately? After finding at C, I'm going to repeat the experiment on the electron. I'm going to find it at C because it didn't get time to spread out again. So if you keep measuring it 1, 2, 3 times, immediately, you will find it again at C, again at C, again at C. Actually, there is a very nice animation that shows what happens for that purpose. So basically, but looks like it's okay. Okay, I have to. Okay, here it is. If you look here, this is a kind of a wave, okay, that is changing with time. Now, what if the same wave, I keep measuring it as here, at very, very small intervals. I'm keeping it in the same position because I'm measuring it again and again and again. If you give it time, look here, the time interval of the measurements is big. You can see that it's changing its position. It's jumping from one place to another place. So if you give it time, it's going to change its shape and position. But if you keep measuring it, as we do in this case here, okay, you can see that we are keeping it in the central spot without being able to move to anywhere. So that's so interesting. Again, okay, so measuring, as I said, measuring it many times is a kind of keeping it in the same point for a very for as long as you repeat the measurements. By the way, they call this kind of effect, they call it Zeno effect. When you make a measurement many times immediately and keep the particle where it is. Okay, so again, I think we talked about that already, that you have basically a wave, and that wave, how we determine the position. We determine the position using the amplitude, and what position we can find when we make the measurement. We know that from the amplitude of the wave. So before making a measurement, it's a wave. After making the measurement, it's gonna collapse and becomes a particle. Sometimes بحب أمثل الموضوع لما أشرح للطلبة أقول لهم this looks like a sponge. عارفين السبونج اللي هي بسم الله الرحمن الرحيم، السفنجة. كأنه عندي سفنجة كده بتتمدد يعني. فقبل ما make a measurement كأني عندي سفنجة متمددة في السبيس. والإلكترون فين؟ It's like everywhere within السبونج دي. لما باجي اعمل ميجرمنت السبونج دي كلها بتكولابس وبتتحول الى نقطه. فاصبح my electron is like at a point. What if I leave it? I release it. السبونج هترجع تتمدد تاني and converts to a wave. But it will change its place and shape. يعني سفنجة عجيبة شوية، تغير شكلها وهتغير وضعها كمان ومكانها فين. ف you can think of it as a kind of a crude model, but يعني you may think of it this way. Good. طبعا دكتور هشام اتكلم على uncertainty. If you know very well, that's another thing that's controversial about quantum mechanics, is that if you know the position very well. يعني انت لو عندك ويف والويف دي متمددة في المكان قوي كده كويس، فانت في الحقيقة بتعرف كويس قوي. احنا لو رجعنا كده هنلاقي في حاجة غريبة. هنلاقي انه if you look at this formula, which we call it de Broglie formula, if you look at it, you can see that the momentum of the wave of the particle is equal to h over lambda. If you keep an eye on p and lambda, they are inversely proportional. If p is big, lambda is small. If lambda is small, if lambda is big, p is small. So that's what takes us to the next thing, which is that so p is the momentum of the particle to be, and lambda is the wavelength of the wave. It describe the electron. Now the thing is انه الuncertainty principle بتتعامل مع الموضوع ده. فبتقول ايه؟ لو انا عندي if you have a wave that's expanded over a very big space, you most probably will know the lambda very well. اللامدا very well معناها انه انا البي معروفه كويس قوي. يعني انا بقيت عارف البوزيشن سوري المومنتم كويس قوي. ليه؟ لان انا لو عارف لامدا كويس جدا، لو عندي معلومه مؤكده عن لامدا، فانا عندي معلومه مؤكده عن بي، لانه بي هي h over lambda. So if I know lambda very well, I know p very well. We know lambda very well if we basically if we have a big wave expanded over a big space. So I can determine lambda very well. So I know the momentum very well. In that case, I don't have good information about the position. ليه؟ لأنه الويف ممتدة over a very big space. If that's the case, then actually أنا مش عارف هي البارتيكل فين. معلوماتي عن البارتيكل مكانها قليل جدا because I have a very expanded wave. But if the wave is very limited to a very small region of space, you end up having a very well information about the position, but not about lambda. And that means you have less information about a lambda. And that's what we usually call it the Heisenberg uncertainty, where delta x times delta b is h over greater than or equal to h over 4 pi. I don't want really to take time talking about that because it's kind of, I mean, not important at this point. Now, why? Okay, so that's all like introductory about how quantum particles or quantum world works. Quantum world works in a way that actually shocks us. We don't used to have such things. No one can tell you if you have a ball in the room, you cannot determine its position, or you cannot follow up its progress at all. So anyway, so what we would like to talk about, I'm gonna talk about this briefly. The next thing is, as I said, Schrödinger equation is the most important thing that happens in quantum mechanics. It's the controlling mechanism of what happens in quantum mechanics. As I mentioned before, you know, basically, as I said, Schrödinger equation takes from you psi 0 and tells you what's going to be psi at a time t later. If we know psi at any time t later, from that we can get all information about the system. So if you remember, before we said if we get x as a function of t for a classical system, you can get everything, like the momentum, the kinetic energy, the potential energy, everything about here. If you know psi of t, you can get all the information about the system at time t. Now, I'm not going to go to the details, but this is how the original Schrödinger equation looks like. It's a second order differential equation, as I said. We usually apply to it what's called separation of variable method, which splits this into two equations. So after some math, okay, after some math, you end up actually with another equation. Okay, so this equation, if you look at it, it has a time here inside, but we can split the time in, out, and we end up with another equation that we call it the time independent Schrödinger equation. Where we remove the time from it. So it's basically gonna give us only psi as a function of x as an answer. Here, as I mentioned before, that's the potential energy of the particle. So this is my potential energy of the particle I'm studying. I would like to show you something. I'm gonna jump to something here. So there are so many calculations, and I'm gonna leave that in my presentation actually for whoever. So when I submit that to the school administration, I'm gonna just leave that for them. You can look at the other things, but I'm gonna jump here to this specific case. What we have here is basically a particle that is living inside what we call it a potential well. يعني عندي infinite square well, بئر عميق مربع. كأني حاطط particle جوه بئر عميق. This is one of the most studied يعني systems that we do in quantum mechanics. It's a kind of exaggerating system where we are basically assuming something that is simple, but at the same time, actually, many of the real physics systems can be can use this to model it. So
Excuse me.
anyway, yeah.
حضرتك بتكتب ولا ايه؟
Oops, just a second. أنا رايح لهناك. I think I didn't go to the right slide. ثانية واحدة. Okay, can you see it now?
اوكي.
Yeah.
Go ahead.
شكرا يا دكتور زيدان، ده انت بتفولو وتوريني اذا في حاجه مش شغاله. شكرا، بارك الله فيك. Thank you so much. Okay, can you see it now? I have this well, okay, the infinite square well. شايفين ده كأنه عندي very
Go ahead.
very deep well, and inside that well, I have a particle, and that particle is living inside that well. And we use Schrodinger equation to solve for that system. When we do this, this is how the potential is described for this particle here. كأني حابس particle جوه بئر عميق. فجوه البئر ما بين 0 و A أنا عندي البوتنشال هو 0. ما فيش أي حاجة. البارتكل حرة جوه. بس عندي أسوار السجن اللي هي الويل walls. شايفين؟ دول they prevent the particle from going out. فأنا لما بروح عند النقط دي كأنه عندي حيطة ارتفاعها infinity. This is one of the most famous models in quantum mechanics. When we solve that using Schrodinger equation, we actually, okay, so as I told you, when we solve Schrodinger equation, usually, you know, in the past, okay, so I'm gonna go back quickly here and show you that, okay. Again, I'm putting some effort here to explain quantum mechanics in some detail because I think you guys need to read about that to understand where the main idea is coming from. Because there is no point that you jump to something that you don't understand the basis of it. So anyway, this is the Schrodinger equation that depends on time. As I said, we split it. We put it into 2 pieces. And that's a very standard way to do partial differential equations. So what happened here is that we split it into 2 pieces. If you guys look here, that's one piece that depends only on time, and that piece depends only on x. So this is like related to the time, and this related only to x. So it's like I'm splitting my original wave function into 2 pieces. This is the original one. I'm splitting it to one in x and another one in t. And it's like I split the progress in position and the progress in time into 2 pieces. Why are we doing that? Because that simplifies how we can solve things. Anyway, when we when we focus on this one, so the first one has a simple solution that depends on t. But this one needs to insert the potential here so you can solve it. As we saw already, okay, in this problem here, I'm solving Schrodinger equation that has no time inside it. So what does it give us? Okay, if you go and do this one, okay, what you are gonna get is basically the following. I have this Schrodinger equation, no t there, no time. Okay, and what you gave it is basically the potential, V. And it's gonna give you out the psi. Psi is a function of x only. And it's gonna give you the energy, possible energies of the particle. So E, it's gonna give you psi and the E. It's gonna, so when we solve Schrodinger equation that doesn't have time in it, you gave it basically the potential energy of your particle, and it's gonna give you out the wave function and the energy of that particle. The surprise is, and that's the very important part that we have to keep in mind, when you make the complete solution, you get something interesting. That the Schrodinger equation that we are working on is gonna give us, so Schrodinger equation that we solve it when we gave it V as a function of X, it's actually not giving me only one psi. It's giving me psi 1, psi 2, psi 3, many solutions. And it's giving me a corresponding energies as well, E1 and the E2 and the E3. So when we solve Schrodinger equation, we get many wave functions and many energies, okay? Every one of those is corresponding, it has a correspond, so it's like, I'm here saying, oh, look, I have basically,
Yes, Dr.
yeah.
Jihad, change the slide. I think you discussed another slide.
Oh, okay. Yes, probably you're right. Sorry. Yeah. So here is, I'm sorry. You have Schrodinger equation, and when you feed it with the potential of that particle, you get actually psi1, psi2, psi3 as solutions for Schrodinger equation. And each one of them, I hope you can see me now. And each one of those guys, okay, so this solution has an energy corresponding to it. Psi2 has a corresponding energy to it. Psi3. So every solution has an energy for the particle. But the surprise is not all the energies are allowed. If you look at this expression here, you can see that I have psi n. N takes values 1, 2, 3, 4, and so on. And En also takes, N here also takes values 1, 2, 3, 4. And that is telling me something, that inside this quantum well, my particle actually can live in what's called the energy level, specific energy levels. That's the thing. Energy level n equals 1 will have this wave here, wave function here, and basically n equals 2, 3, 4. So I'm going to have here, if we look, if the solution gives me this wave function, I'm going to be basically using this psi1, and the corresponding energy is E1. So if you put n here equals 1, you get E1, which in that case, if n is 1, it's going to be pi squared h bar squared over 2ma squared, where a is the width basically of the width عرض بتاع الويل, وm هي الماس بتاعت البارتكل, وpi وh are constants. Now, if you try to put n equals 2, you are going to jump to a new state, E2 here, where the wave function will look like that. And basically, E2, if you put n, so this is n equals 1, but if you put n equals 2, you're going to get the same guy, but multiplied by 4. Okay, so this is basically what you're going to get. Between E1 and E2, between these two guys, between the two levels دول, you are not allowed to put any particle. I mean, particle مش مسموح لها تاخد أي energy between E1 and E2. ممكن تنط من E1 ل E2 وبعدين تقفز إلى E3 كمان. And that's very important because this is very much related to what we are going to do in quantum computing. So basically, when you solve the problem, you get certain energies that are allowed. Your particle can take these energies, but not between them. And in each, in each one of those states, you're gonna basically have, so this is, for instance, wave 2. And then here you get wave 3, and so on. So each solution for Schrodinger equation is going to give you a different energy, and those what we call them allowed energies, طاقات مسموح بيها. فأنا البارتيكل بتاعتي can live in this level, or this, okay, can live in this level. Let me show you. Can live here, أو هنا أو هنا أو هنا, بس cannot live in between. ما تقدرش تعيش بين الاثنين. Okay? So this is a very important thing in quantum mechanics. When we solve, لما أقول لك مثلا أنا عندي particle جوه potential well, عندها مستويات للطاقة مسموح بيها. الموضوع يبدو غريب. ليه غريب؟ فكر في الآتي. تخيل نفسك في عندك كورة جوه غرفة مثلا. Okay? Imagine that you have basically كورة، والكورة دي موجودة جوه غرفة. فأنا لو أنا عملت كده وقلت ده كلاسيكال، اوكي، وأنا عندي basically كورة، والكورة دي هنا، اوكي، so this is a ball، وأنا بقول أنا هشوت الكورة دي مثلا، هديها دفعة بفورس اف مثلا. معنى اللي انا بقوله ده انه انا لو هطبق قوانين الكوانتم ميكانكس هنا، معناها ان الكرة دي مثلا ممكن تمشي بسرعة 1 meters per second، او تمشي بسرعة 2 meters per second مثلا، او 3 meters per second. ده معنى الكوانتايزيشن، انه انا مش مسموح لي مثلا، ما ينفعش ان انا عندي كوره مثلا عندها 2.5 او 1.5 meters per second. اوكي، ده not allowed. not allowed. فانا في الحقيقه بيحصل حاجه غريبه، انه بقى عندي شروط. لو انا قلت ان ده بيحصل في الكلاسيكال ميكانكس او في الحياه الطبيعيه، you will not accept it. You would say لا طبعا انا I can put يعني اي فورس تعجبني واخلي البارتكل تتحرك بالسرعه اللي انا اختارها، اي حاجه مسموحه. In here, as we saw, that's not the case. In quantum mechanics, it's very weird. انت في الحقيقه البارتكل بتاعتك مش مسموح لها تاخد اي انرجي، لا انرجيز معينه فقط هي اللي مسموحه. اوكي، والانرجيز دي كانه انا بقول انا عندي الكترون، بس ممكن يبقى عنده انرجي E1 او E2 او E3، بس لا يستطيع ياخد اي values بينهم. This is so important. Very, very, very important. Okay, so we have what's called quantization. So that's the quantum. The quantum world acts this way. I have here what's called quantization. Okay, quantization. معايا يا جماعة؟ So this is the thing. In classical physics, احنا عارفين ان انا I can give my a ball or an object, I can give it any velocity I wish, which means I can give it any kinetic energy I wish, which means I can give it any momentum I wish. But in the quantum case, if you have a particle under a certain potential, it can have only certain specific energies, not in between them. That's what is amazing. Why this is important? Because actually في الفيزيكس في اللي احنا بنعمله بعد كده، again I'm jumping دلوقتي. يعني انا ده كنت بعمله as an introductory part يا جماعه. في حسابات كتير قوي وحاجات معموله بتتكلم بقى على البارتيكل دي اللي جوه الويل، وشويه ماث وحاجات كده. I'm not gonna go over them. Whoever is interested can see them in my slides when I give it to the guys here. But the thing is, I want to jump why this is important for us. Now that takes us to the quantum computing. How is that? The thing is, we have the classical bit and the quantum bit. The classical bit, okay, is a system that basically, okay, it's like a transistor. You have a transistor that allows a current to go through, so we call that a value of 1. Or it prevents a current from going through، يعني تمنع الكرنت يمر، فبنقول الترانزستور ده كأنه شايل فاليو 0. فالكلاسيكال بت بتشيل 1 أو 0، ممكن أحملها برقم 1 أو رقم 0. The thing is here في الكوانتم بت أنا بالظبط كأنه عندي سيستم. اوكي، السيستم ده احنا شفنا قبل كده في الانفينيت سكوير ويل ان انا ممكن اكون عندي basically العديد من الستيتس. اوكي، عندي الليفل الاول، الثاني، الثالث، الرابع، الخامس، وبعدين السيستم بتاعي. اوكي، يعني ده ان 1 2 3 4 5، وانا البارتكل اللي جوه الويل ممكن تعيش في اي واحد من دول. ممكن basically تعيش هنا او هنا او هنا، في مكان منهم، يعني تختار مكان وتعيش بينه. ماذا لو اني انا عندي ويل، والويل ده بس ما فيهوش غير 2 states، 1 و2، فالبارتكل تقدر تعيش هنا او تعيش هنا. اوكي، فانا كاني شلت كل لغيت كل الستيتس اللي فوق وما عنديش غير 2 levels بس. This is gonna make for me a qubit. Okay, this is gonna make for me a qubit. ازاي؟ انا عندي two levels والparticle بتاعتي if it's in the ground state, okay, I'm gonna call that zero. شايف؟ ولو حطيتها الجراوند ستيت اللي هو الستيت اوت ستيت اقل ستيت, if I put it there, okay, it's gonna stay there and I'm gonna call that this system is in a zero state. كأنه شايل is keeping a zero information. On the other hand, if I make the particle jump to the upper state, it's now gonna be called one. Okay, see? But the thing is, in quantum mechanics, actually, I can make the particle live between the two states at the same time. So it's a kind of a combination of being in the zero and the one at the same time. So that is the big advantage of quantum systems, that you can have what's called a combination of states. You can make your particle living in the ground state. You can make it live in the upper state. We have quantization, so there is a gap in the middle. But I can make it live in the ground state, so that's zero. It's like I'm now storing a zero information, a zero number, or I'm gonna put it in the upper state, so that's now like I'm storing one. And the big advantage of quantum mechanics is that you can make it live between two states. How is that? Why it's living between two states? That's very weird. I'm gonna explain that in my next lecture because I'm running out of time already. But this is where we are gonna start next time, inshallah. Dr. Zidan.
Thank you, Professor. If you have time for more questions. If you have time for
yeah, sure. Yeah, I'm here. I can take a few questions, inshallah.
اتفضل بس قول عشان اوضح السؤال.
طيب السؤال الاول لو انا هو هسال في الباص يعني لو انا عملت فيرست ميجرمنت للالكترون ولقيته عند بوينت A وعملت سكند ميجرمنت لقيته عند بوينت B, ليه اقدر اشيوب ان هو ترانسفير؟
طيب في سؤال I think انه very good question. اسمك ايه؟ في ضحى بتسال بتقول لحضرتك لو هي عملت